100 million years ago, Earth was not the world we know today. There were no permanent ice caps at the poles, no glaciers grinding their way across continents, no frozen oceans locking sunlight away beneath white armor. Instead, the planet existed in a greenhouse state so intense and so prolonged that winters, as we understand them, were almost meaningless. This was an era when summers never truly ended. To understand this world, we must first abandon the mental image of modern Earth. Today, our planet operates under a delicate climatic balance, shaped by polar ice sheets in Antarctica and Greenland. These frozen regions reflect sunlight back into space, helping regulate global temperature. They act as stabilizers in Earth's climate system. But in the mid-Cretaceous period, those stabilizers did not exist. At that time, atmospheric carbon dioxide levels were dramatically higher than they are today. Geological evidence suggests concentrations may have reached between 1,000 and 2,000 parts per million, several times pre-industrial levels. This was not the result of human industry. It was driven by tectonic forces operating deep beneath the planet's surface. Earth's crust was in motion. Massive plates were drifting apart as the supercontinent of earlier ages continued to fragment. Although the great landmass of Pangaea had already broken up long before the Cretaceous, its legacy shaped the configuration of continents. North America was separating further from Europe. South America was drifting away from Africa. India was racing northward toward Asia. These movements were not silent. They were accompanied by intense volcanic activity along mid-ocean ridges. As seafloor spreading accelerated, magma rose continuously from beneath the crust. This process released enormous amounts of carbon dioxide into the atmosphere. Volcanic arcs and large igneous provinces added even more greenhouse gases. Over millions of years, the accumulation of carbon dioxide thickened the atmospheric blanket surrounding the planet. Heat that would normally radiate back into space was trapped. Global average temperatures rose significantly. Estimates suggest that the planet was between 6 and 14 degrees Celsius warmer than it is today. But averages conceal the most astonishing fact of this era. The poles were warm. Forests grew within the Arctic Circle. Rivers flowed through what is now Antarctica. Instead of ice sheets, there were swamps and dense vegetation. Without ice caps, Earth's albedo was reduced. Less sunlight was reflected away. Darker ocean surfaces absorbed more heat. This created a feedback loop that reinforced warmth. The oceans expanded as they heated, raising global sea levels by as much as 200 meters above modern levels. Entire regions that are now dry land were submerged beneath shallow inland sea. North America was divided by the western interior seaway, a vast body of warm water that stretched from the Gulf of Mexico to the Arctic Ocean. Europe existed as an archipelago of islands. Africa was partially flooded along its margins. Coastlines were dynamic, shifting with thermal expansion and tectonic uplift in this greenhouse world. Seasons still existed in a technical sense. The tilt of Earth's axis had not changed significantly, but temperature contrasts were muted. Winters were mild, even at high latitudes. Snow, if it fell at all in polar regions, melted quickly during extended summers of continuous sunlight. Fossilized tree rings from high latitude forests reveal something remarkable. They show growth patterns consistent with long periods of darkness followed by intense growth during prolonged daylight. This indicates that plants adapted not to cold winters, but to light cycles. The challenge was not freezing temperatures, but surviving months without sunlight. Imagine standing near the North Pole. 100 million years ago, during summer, the sun would circle the horizon without setting. The forests of conifers and early flowering plants would stretch toward the horizon. Dinosaurs would roam through river valleys beneath golden skies that never dimmed. Temperatures might resemble those of modern temperate regions rather than Arctic tundra. During winter darkness, temperatures would drop, but rarely to extremes. There is no evidence of permanent ice sheets in these polar regions during the height of the Cretaceous greenhouse. Instead, ecosystems endured through metabolic adaptation and behavioral changes. This climate stability created a planet of extraordinary biological productivity. Warm temperatures accelerated chemical reactions in soils and oceans. Higher carbon dioxide levels enhanced photosynthesis for many plant species. Forests grew thick and fast. Ferns carpeted floodplains. Early flowering plants diversified rapidly, reshaping terrestrial ecosystems. With abundant plant life came abundant herbivores. Dinosaurs thrived in this environment. Their growth rates, inferred from bone histology, suggest rapid development supported by plentiful food. Long growing seasons allowed ecosystems to sustain massive populations of large-bodied animals. In the oceans, warmth transformed circulation patterns. Modern oceans rely partly on cold, dense water sinking near the poles to drive global thermohaline circulation. But in a world without polar ice, and with warmer high-latitude waters, this circulation system operated differently. Temperature gradients between equator and poles were weaker. Heat distribution was more uniform across the planet. This equable climate meant fewer extreme storms driven by temperature contrasts, but it also meant that tropical conditions extended far beyond their present boundaries. Coral reefs flourished at latitudes that would today be considered temperate. Marine biodiversity expanded into regions now too cold to support such life. However, endless warmth was not synonymous with permanent tranquility. The greenhouse state contained instabilities beneath its surface. At high ocean temperatures reduced the solubility of oxygen in seawater, combined with increased nutrient runoff from weathering continents. This sometimes triggered oceanic anoxic events. During these intervals, large portions of the deep ocean became depleted of oxygen, leading to widespread marine die-offs. Layers of black shale found in marine sedimentary rocks record these episodes. They are geological fingerprints of times when the oceans struggled under excessive warmth and nutrient loading. Yet life repeatedly recovered. The resilience of Cretaceous ecosystems was remarkable. On land, Atmospheric circulation patterns differed from today. Without strong polar cooling, the jet streams were weaker. Rainfall distribution was shaped by monsoonal systems intensified by warm seas. Some continental interiors may have experienced seasonal dryness, even as global temperatures remained high. The greenhouse climate also influenced evolutionary trajectories. Warm conditions at high latitudes allowed species to disperse widely across continents. Faunal similarities between regions that are now climatically distinct were more common. Polar forests served as corridors for migration rather than barriers. This was a world where climate gradients were gentle. The equator was warm, but not lethally so. The poles were mild. The difference between them was smaller than today. Life occupied nearly every available niche. Geochemical evidence from oxygen isotopes preserved in marine fossils provides quantitative confirmation of these temperatures. The ratio of oxygen 1:8 to oxygen 16 inches shell material reflects the temperature of seawater at the time of formation. Analyses consistently indicate elevated ocean temperatures even at high latitudes. Mean annual sea surface temperatures near the poles may have exceeded 15 degrees Celsius. Imagine swimming in waters near the Arctic Circle that feel more like those off the coast of modern Northern California. This was not a brief anomaly. It persisted for millions of years. The greenhouse Earth was sustained by a balance between carbon inputs and carbon removal processes. Volcanic outgassing supplied carbon dioxide. Weathering of silicate rocks slowly removed it by converting atmospheric carbon into carbonate minerals that were eventually buried in sediments. But during peak tectonic activity, inputs outpaced removal. Over long timescales, Earth's climate system self-regulates through these geological feedbacks. But the timescale is measured in hundreds of thousands to millions of years. Within the span of human civilization, such adjustments would appear imperceptibly slow. In the Cretaceous, carbon cycling reached a new equilibrium at a warmer baseline. Ice sheets require sustained low temperatures to form and persist. Once eliminated, their absence reinforced warming through albedo feedback. The planet settled into a stable greenhouse mode. Yet, even within this stability, there were fluctuations. Short-term cooling intervals occurred, possibly linked to changes in volcanic output or orbital cycles. But these were minor variations against a backdrop of pervasive warmth. The biosphere responded dynamically. Plant communities adapted to elevated carbon dioxide. Leaf morphology from fossil records shows larger average leaf sizes in some regions, consistent with warm, humid conditions. Stomatal densities on fossil leaves provide indirect measures of atmospheric carbon dioxide, and they align with geochemical reconstructions of elevated levels. Animal physiology also adapted. Some dinosaurs inhabiting polar regions exhibit bone structures suggesting year-round residency rather than seasonal migration. This implies that even during extended darkness, conditions remained survivable. The absence of polar ice also meant higher sea levels. Continental shelves were submerged, creating vast, shallow marine habitats. These environments are among the most productive ecosystems on Earth. Plankton thrived in sunlit waters, forming the base of complex marine food webs. The expansion of shallow seas also influenced climate further. Water has a high heat capacity. Extensive epicontinental seas acted as thermal buffers, absorbing heat during warm periods and releasing it slowly. This dampened temperature extremes and reinforced the equable climate. If we were to observe this world from space, it would appear different in subtle but profound ways. Coastlines would be unfamiliar, and polar regions would be green rather than white. The cloud patterns would reflect altered atmospheric circulation. The planet would radiate heat differently due to its thicker greenhouse blanket. And yet, beneath this surface of endless summer, tectonic forces continued their slow rearrangement of continents. The seeds of future climatic shifts were already being sown. The greenhouse Earth of the mid-Cretaceous represents one of the warmest sustained intervals in the last 500 million years. It demonstrates that Earth's climate is not fixed, but capable of occupying radically different states depending on atmospheric composition and tectonic configuration. For millions of years, life flourished under these conditions. Ecosystems were diverse and abundant, evolutionary innovation accelerated, flowering plants spread across landscapes, transforming food webs, insects diversified alongside them. Dinosaurs reached ecological dominance in nearly every terrestrial environment. This was not a fragile paradise. It was a robust, adaptive biosphere shaped by warmth, but its stability depended on geological forces that operate beyond the scale of individual lifetimes. As Chapter 1 closes, we are left with a portrait of a planet transformed. No ice at the poles, seas encroaching upon continents, forests growing under polar suns, oceans warm and expansive. A climate state sustained by volcanic breath and tectonic motion. It was an Earth unfamiliar to modern eyes, yet entirely natural within the planet's long history. The era when summers never ended was not myth or exaggeration. It was a scientifically documented chapter in Earth's deep past, and in understanding it, we gain perspective on the power of greenhouse climates, the resilience of life, and the dynamic systems that govern our planet. The story has only begun. The oceans of the greenhouse world were not merely bodies of water surrounding continents. They were the dominant force shaping climate, chemistry, and life on Earth. In the era when summers never ended, the seas expanded across the planet, swallowing coastlines and carving continents into archipelagos. Beneath their warm surfaces, evolution accelerated, ecosystems flourished, and instability quietly gathered strength. During the mid-Cretaceous, global sea levels were among the highest in the last half-billion years. Without polar ice sheets locking water away, and with ocean basins swollen from thermal expansion, sea levels rose more than 150 to 200 meters above modern levels. This transformed geography entirely. North America was split in two by a vast inland sea. This body of water, known today as the Western Interior Seaway, stretched from the Gulf of Mexico to the Arctic Ocean. It divided the continent into eastern and western landmasses for millions of years. Its waters were shallow, warm, and rich in life. Europe was fragmented into islands scattered across tropical seas. Africa's margins were drowned beneath shallow marine shells. South America and Africa, once joined, were drifting apart as the South Atlantic widened. India, still isolated, raced northward across the Tethys Ocean. These shallow seas were biological engines. Sunlight penetrated easily to the seabed in many regions, fueling plankton growth. Phytoplankton formed dense blooms in nutrient-rich waters. Zooplankton followed. Small fish fed on them. Larger predators hunted the fish. Entire food webs cascaded upward from microscopic photosynthetic organisms. Warmer oceans altered the chemistry of seawater. Temperature directly influences gas solubility. As seawater warms, its capacity to hold dissolved oxygen decreases. This simple physical principle had enormous biological consequences. In parts of the Cretaceous Ocean, oxygen levels declined significantly, especially in deeper waters. These conditions sometimes triggered what geologists call oceanic anoxic events. During these intervals, large volumes of the ocean became depleted of oxygen. Marine organisms that depended on well-oxygenated waters struggled or perished. Organic matter that would normally decompose instead accumulated on the seafloor, eventually forming thick layers of black shale. These black shales are preserved today in sedimentary rock formations across the world. They are chemical records of ancient ocean stress. Yet even these events did not permanently disrupt the greenhouse climate. They were episodes within a broader system, sustained by high atmospheric carbon dioxide. The greenhouse oceans were stratified differently from modern oceans. Today, cold polar waters sink and help drive global thermohaline circulation, redistributing heat across the planet. But in the Cretaceous, polar waters were not cold enough to sink in the same way. Temperature gradients between equator and poles were weaker. Circulation patterns were slower and less vigorous. This had profound implications. Sluggish circulation meant that deep waters were less frequently replenished with oxygen-rich surface water. This contributed to oxygen depletion at depth. At the same time, surface waters remained warm and productive. The Tethys Ocean, which separated the northern and southern continents, was a tropical marine highway. Its warm currents connected ecosystems across vast distances. Coral reefs flourished along its margins. Carbonate platforms built up over millions of years, forming thick limestone deposits that remain visible in modern mountain ranges. Coral reefs in the Cretaceous extended far beyond the tropical latitudes where they are confined today. Warm conditions allowed reef-building organisms to thrive at higher latitudes. These reefs supported extraordinary biodiversity, including fish, mollusks, crustaceans, and marine reptiles. Among the dominant predators of these seas were mosasaurs. These large marine reptiles evolved from land-dwelling ancestors and adapted fully to life in the water. Their streamlined bodies, powerful tails, and double-hinged jaws made them formidable hunters. Ammonites spiraled through the water column in immense numbers. Their coiled shells varied in size from a few centimeters to over 2 meters in diameter. These cephalopods were both predators and prey, forming a critical link in marine food webs. Their rapid evolution and widespread distribution make them valuable index fossils for dating Cretaceous rock layers. Large predatory fish such as Xiphactinus patrolled the inland seas. Some fossils preserve smaller fish within their stomach cavities, captured in moments frozen by time. Sharks, already well established in marine ecosystems, diversified into new forms. The warmth of the oceans influenced global climate beyond marine ecosystems. Warm water evaporates more readily than cold water. But maybe increased evaporation intensified the hydrological cycle. Moisture-laden air masses traveled over continents, delivering rainfall that sustained lush vegetation even in high latitudes. This intensified water cycle also enhanced chemical weathering of rocks on land. Rainfall reacts with carbon dioxide dissolved in water to form weak carbonic acid. This acid weathers silicate rocks, gradually removing carbon dioxide from the atmosphere and transporting it to the oceans as dissolved ions. There, it can precipitate as carbonate minerals and become locked into sedimentary rock. Thus, even in the height of greenhouse conditions, long-term feedback mechanisms were at work. The oceans acted not only as heat reservoirs, but also as carbon sinks. Microscopic marine organisms, such as coccolithophores, built shells from calcium carbonate. When they died, their shells sank to the sea floor, contributing to thick chalk deposits. The white cliffs of Dover in England are composed largely of these microscopic remains from the Cretaceous sea. Yet the ocean's ability to absorb carbon was not limitless. The periods of intense volcanic outgassing overwhelmed these sinks, driving further warming. Large igneous provinces erupted vast quantities of lava and gas over relatively short geological intervals. Each episode injected additional carbon dioxide into the atmosphere. The greenhouse ocean was a paradox. It supported some of the most diverse and productive ecosystems in Earth's history. At the same time, it was chemically unstable in ways that occasionally threatened marine life. Temperature reconstructions from oxygen isotopes in marine fossils show sea surface temperatures in tropical regions exceeding 30 degrees Celsius. Even high-latitude seas may have remained above 15 degrees Celsius year-round. Such warmth would have dramatically altered species distributions compared to today. Marine reptiles extended their ranges toward the poles. Fossil evidence from high latitudes indicates that large predators inhabited regions that are now frigid. The absence of ice allowed open ocean connections across polar regions, facilitating dispersal. The Western Interior Seaway provides a detailed snapshot of this marine world. Its sediments preserve fossils of fish, sharks, turtles, plesiosaurs and mosasaurs. It was not a static body of water. Its extent fluctuated with global sea levels and regional tectonics, but for millions of years it remained a central feature of North American geography. Life within this seaway adapted to warm, shallow conditions. Plankton blooms lightly colored the water during peak productivity. Storms stirred sediments from the seafloor. River systems delivered nutrients from surrounding land masses. The greenhouse ocean also influenced atmospheric circulation. Warm surface waters released latent heat into the atmosphere, fueling storm systems. While temperature gradients were weaker than today, tropical cyclones may have been intense due to elevated sea surface temperatures. The lack of polar ice meant that there was no seasonal sea ice formation to regulate heat exchange. Open polar waters absorbed solar radiation during extended summers. During polar winters, heat stored in the ocean was gradually released back into the atmosphere, preventing extreme cooling. This coupling between ocean and atmosphere created a relatively stable, equable climate. Extremes existed locally, but global temperature differences were muted compared to modern patterns. However, the stability of the greenhouse world depended on a delicate balance of feedbacks. As carbon dioxide levels rose, weathering rates increased, slowly drawing down carbon over millions of years. As temperatures increased, biological productivity in some regions accelerated, potentially enhancing carbon burial. But feedbacks can lag behind forcing. During intervals of rapid carbon injection, such as large volcanic episodes, the climate system could overshoot. Oceanic anoxic events are likely manifestations of such overshoot conditions. These events had evolutionary consequences, and marine extinctions occurred regionally. Ecological niches opened and were refilled. Diversity patterns shifted. Yet the overall trajectory of life in the Cretaceous remained upward in complexity and specialization. One of the most striking aspects of the greenhouse ocean is how it challenges modern intuitions. Today, we associate warm oceans with coral bleaching and ecosystem stress. But in the Cretaceous, coral reefs thrived under higher temperatures and higher carbon dioxide levels than today. This does not mean that modern ecosystems are immune to change. It means that species existing then were adapted to those baseline conditions over millions of years. Evolution operates within environmental context. The marine organisms of the Cretaceous had evolved under greenhouse conditions. They were not transitioning rapidly from a cooler baseline. They were the products of that warm world. As millions of years passed, sediments accumulated on the sea floor. Chalk deposits thickened. Organic rich shales recorded anoxic episodes. Tectonic plates continued drifting. Gradually, the configuration of ocean basins evolved. Gateways opened and closed, altering circulation patterns. Toward the later Cretaceous, subtle shifts began to influence ocean chemistry and climate. But during the peak greenhouse interval, the oceans were vast, warm, and biologically vibrant. If one could descend into the western interior seaway on a summer day 100 million years ago, sunlight would stream through clear water. Schools of fish would dart above carbonate sand. Ammonites would drift, propelled by jet-like pulses in deeper waters. Mosasaurs would glide silently, their eyes scanning for movement. Above the surface, coastal plains would shimmer with heat. Distant thunderstorms would rise along humid horizons. The boundary between sea and sky would blur in a world defined by warmth. The greenhouse ocean was not a backdrop to terrestrial life. It was the central climate regulator, the carbon processor, the engine of hydrological cycles, and the stage for marine evolution. Its expansion reshaped continents, its chemistry recorded planetary change, its warmth defined the era. And yet, even in this age of endless summer, the forces that sustain warmth can also contain the seeds of transformation. The ocean remembers everything. In its sediments, in its isotopes, in its fossils, it preserves the story of a planet in greenhouse equilibrium. As we move forward, we will leave the seas and travel toward the ends of the Earth to polar forests that thrived under months of sunlight and darkness. The greenhouse world extended even to the pole. The summer truly never ended. At the very edges of the world, where modern maps show endless white ice and temperatures that plunge far below freezing, the greenhouse Earth told a different story. During the height of the Cretaceous, the polar regions were not frozen wastelands. They were living landscapes. Forests grew beneath months of uninterrupted sunlight. Rivers flowed freely across ground that today lies buried under kilometers of ice. This was the most radical expression of a planet without winter. To understand how extraordinary this was, consider the modern Arctic today. It is defined by sea ice, tundra, permafrost, and long, brutal winters. Antarctica is even more extreme. A continent of ice, locked in temperatures that can fall below -80 degrees Celsius. These frozen regions act as Earth's climate stabilizers, reflecting solar radiation and driving deep ocean circulation. But in the mid-Cretaceous, neither polar region hosted permanent ice sheets. Geological evidence confirms the absence of glacial deposits from this interval. Sedimentary records lack the telltale scratches and debris associated with continental ice. Instead, they contain fossilized wood, pollen grains, and even the remains of dinosaurs. Antarctica, now synonymous with ice, once supported temperate rainforests. Drill cores extracted from beneath the modern ice sheet reveal preserved root systems, fossil soils, and plant spores dating back roughly 90 million years. Isotopic analysis of these sediments indicates mean annual temperatures far above freezing. Summer temperatures may have reached 15 to 20 degrees Celsius, even at latitudes close to the South Pole. The Arctic told a similar story. Fossil forests discovered in northern Canada and Alaska revealed dense stands of conifers, ginkgos, and early flowering plants. Growth rings in fossilized wood provide detailed climate data. Unlike trees in strongly seasonal climates, these polar Cretaceous trees show relatively modest ring contrasts, consistent with mild winters and long growing seasons. However, there was one dramatic seasonal factor that could not be eliminated: light. The tilt of Earth's axis, approximately 23.5 degrees, has remained relatively stable over geological time. This means that polar regions still experienced months of continuous daylight in summer and months of darkness in winter. In a greenhouse world, the challenge at high latitudes was not freezing cold, but the absence of sunlight for extended periods. How did ecosystems survive such darkness? Plants adapted through metabolic strategies. During continuous summer daylight, photosynthesis operated almost without interruption. Rapid growth occurred during these bright months. Energy was stored in roots and woody tissues. During winter darkness, growth slowed or stopped, but temperatures remained above lethal thresholds. Fossil evidence suggests that many polar trees were deciduous. Shedding leaves before winter darkness may have reduced metabolic demand. Others were evergreen, maintaining foliage year-round. Both strategies appear to have coexisted. Animal life also adapted to the polar light cycle. Among the most compelling discoveries are dinosaur fossils from high latitudes. These are not merely stray bones transported by rivers. They represent individuals that likely lived year-round in polar environments. Hadrosaurs, small ornithopods, and even larger theropods have been found in Arctic deposits. Bone microstructure analysis reveals growth patterns consistent with permanent residency rather than seasonal migration. This suggests that at least some dinosaur species endured months of darkness each year. The idea of dinosaurs surviving polar winters once seemed implausible. Early depictions of dinosaurs imagined them as cold-blooded reptiles requiring constant warmth. But modern research indicates that many dinosaurs possessed elevated metabolic rates. Some may have been fully endothermic, generating internal heat. Feathers or filamentous coverings in certain species could have provided insulation. Even without extreme cold, darkness posed ecological challenges. Herbivores dependent on photosynthetic plants would have faced seasonal food shortages. Yet the fossil record indicates stable populations. This implies that polar ecosystems maintained sufficient productivity during summer to sustain animals through winter. Rivers and wetlands likely remained unfrozen for much of the year, which groundwater and oceanic influence would have moderated temperatures further. Remember that ocean waters near the poles were significantly warmer than today. Open polar seas released stored heat into the atmosphere during winter, preventing deep freezes. The absence of sea ice is especially important today. Sea ice forms a reflective barrier that limits heat exchange between ocean and atmosphere. In the Cretaceous, open polar waters absorbed solar radiation during summer and slowly released it during winter. This created a thermal buffer. Climate models simulating mid-Cretaceous conditions consistently show weak temperature gradients between equator and poles. While tropical regions were warm, they were not dramatically hotter than today. Instead, the most significant warming occurred at high latitudes. This phenomenon is known as polar amplification. Polar amplification arises because greenhouse gases trap outgoing infrared radiation more effectively in cold, dry air. As carbon dioxide levels rise, high-latitude regions experience disproportionate warming. In the Cretaceous, this effect eliminated permanent ice and allowed forests to colonize the poles. The polar forests were not identical to modern tropical jungles. They were composed primarily of conifers, cycads, ferns, and early angiosperms. Biodiversity was substantial, but distinct from equatorial ecosystems. Insects flourished in warm, humid conditions. Freshwater ecosystems supported fish and amphibians. Evidence from sedimentary deposits suggests that rainfall was abundant. Warm oceans fueled evaporation, and atmospheric circulation delivered moisture poleward. Cloud cover may have been frequent, further moderating temperature extremes. These high-latitude forests functioned as major carbon sinks. Rapid plant growth during extended summers drew carbon dioxide from the atmosphere. Organic matter accumulated in soils and wetlands. Over geological timescales, some of this carbon became buried in sediments, contributing to long-term climate regulation. Yet the greenhouse state persisted for millions of years. This indicates that carbon inputs from tectonic and volcanic sources roughly balanced removal processes. The polar forests were part of a dynamic equilibrium rather than a permanent solution to atmospheric carbon. Antarctica's transformation is particularly striking. Today, its thick ice sheet reflects sunlight and drives global ocean circulation through the formation of cold, dense bottom waters. In the Cretaceous, without ice, Antarctica would have influenced circulation differently. Warm surface waters flowed freely around the continent. Plate tectonics also played a role during the mid-Cretaceous. Antarctica was still connected to South America and Australia to varying degrees. Ocean gateways were narrower or absent. These geographic differences influenced current patterns and heat distribution. As continents drifted further apart in later periods, ocean circulation changed dramatically, eventually contributing to global cooling. But in the greenhouse peak, polar connectivity facilitated warmth retention. The presence of forests near the South Pole challenges assumptions about habitability. Modern climate zones are products of current atmospheric composition and continental arrangement. In the Cretaceous, both were different. What we now consider uninhabitable extremes were once thriving ecosystems. Imagine standing in Antarctica 90 million years ago. Instead of an endless ice plateau, you would see rolling terrain covered in conifer forests. Rivers meander through valleys. Insects buzz in humid air. Small dinosaurs move cautiously between tree trunks. Above, during summer, the sun circles without setting. Winter would bring darkness, but not devastation. Temperatures might dip close to freezing, but prolonged deep freezes were unlikely. Snow, if it fell, would melt with returning light. Ice would be seasonal and thin rather than continental and permanent. Fossil pollen extracted from Antarctic sediments provides detailed reconstructions of plant communities. These microscopic grains are durable and widespread. Their diversity indicates complex ecosystems rather than sparse vegetation. Similar evidence emerges from the Northern Hemisphere. In Alaska's North Slope, fossilized tree stumps remain in growth position, preserved in ancient floodplain deposits. They testify to forests growing at latitudes above 70 degrees north. The polar greenhouse environment reshaped global biodiversity patterns. Migration routes extended through high latitudes. Species distributions were less constrained by temperature barriers. Faunal exchanges between continents were facilitated by land connections and hospitable climates. This does not mean that the polar regions were identical to temperate zones elsewhere. Seasonal light cycles created unique ecological pressures. Growth spurts during summer likely led to bursts of biological activity. Winter dormancy may have synchronized life cycles in distinctive ways. The concept of endless summer is partly metaphorical. Technically, seasons existed, but from a thermal perspective, the absence of prolonged freezing and the persistence of warmth year-round justified the phrase, "The polar regions were no longer domains of ice." Climate simulations indicate that carbon dioxide concentrations above roughly 1,000 parts per million are sufficient to eliminate large polar ice sheets under certain continental configurations. In the Cretaceous, levels likely exceeded that threshold. Combined with favorable tectonic arrangements, this locked the planet into a greenhouse mode. The importance of polar forests extends beyond paleoclimatology. They provide insight into Earth's sensitivity to greenhouse gases. They demonstrate that under sustained high carbon dioxide, even polar ice can vanish. Over millions of years, sedimentation preserved this record. When we drill into Antarctic rock layers and recover fossil wood, we are reading a chapter written in cellulose and lignin rather than ink. As the Cretaceous progressed, subtle shifts began altering global conditions. Volcanic activity fluctuated, and continental drift changed ocean gateways. But for a long interval, polar warmth endured. Life adapted not to survive cold, but to endure darkness. Ecosystems evolved in rhythm with light rather than frost. The greenhouse Earth reached even the ends of the planet. Chapter 3 reveals that the era when summers never ended was not confined to tropical seas or equatorial plains. It extended to the poles themselves. The image of dinosaurs walking beneath polar trees is not fantasy. It is supported by sediment cores, isotopic ratios, fossil pollen, and bone histology. Earth's climate system, when pushed by tectonic forces and greenhouse gases, can transform its coldest regions into temperate realms. The polar forests stand as living proof that winter, as we know it, once vanished from the face of the earth. And in that vanished winter lies a lesson about the power and plasticity of our planet's climate system. If the oceans were the engine of the greenhouse world and the poles its most surprising transformation, then the land was its grand stage. Beneath the sky, thick with greenhouse gases and across continents fragmented by rising seas, terrestrial ecosystems reached extraordinary complexity. This was the age when dinosaurs did not merely survive in warmth, they dominated it. The mid to late Cretaceous marked the ecological zenith of dinosaur evolution. Millions of years of relative climatic stability allowed ecosystems to mature, without the disruption of major global glaciations. Long growing seasons, elevated carbon dioxide levels, and widespread vegetation created conditions that supported immense biomass. In a greenhouse climate, plant productivity can increase under certain conditions. Higher atmospheric carbon dioxide enhances photosynthesis in many plant species, particularly those using the C3 photosynthetic pathway, which dominated during the Cretaceous. Combined with warm temperatures and abundant rainfall driven by intensified hydrological cycles, vegetation flourished. Forests spread across continents. Conifers still dominated many landscapes, but flowering plants were expanding rapidly. Angiosperms first appeared earlier in the Cretaceous and began diversifying at an accelerating pace. Their evolutionary success reshaped terrestrial ecosystems. Flowering plants offered advantages. They produced fruits and seeds that could be dispersed by animals. They grew quickly and adapted to varied environments. Their leaves often had higher nutrient content than many gymnosperms. Herbivorous dinosaurs encountered new food sources, and this botanical revolution influenced evolutionary pressures across trophic levels. Among the apex predators of this world stood Tyrannosaurus rex, one of the most iconic terrestrial carnivores in Earth's history. Although Tyrannosaurus lived toward the very end of the Cretaceous, its lineage evolved within the broader greenhouse context. Its massive skull, bone-crushing bite, and advanced sensory adaptations reflect a predator refined by millions of years of ecological competition. Further south, in river-dominated environments of what is now North Africa, Spinosaurus occupied a unique ecological niche. Unlike Tyrannosaurus, Spinosaurus was semi-aquatic. Its elongated snout, conical teeth, and paddle-like tail indicate adaptation to hunting fish in warm Cretaceous rivers and coastal lagoons. Such specialization illustrates the ecological diversity made possible by stable greenhouse climates. Herbivorous dinosaurs reached extraordinary sizes during this era. Titanosaurs roamed southern continents, their elongated necks sweeping across treetops. Hadrosaurs traveled in herds through floodplains. Ceratopsians, armored with horns and frills, grazed on low vegetation. The abundance of plant life sustained these megaherbivores. Long growing seasons meant that food was available for much of the year. In high latitudes, summer bursts of growth were intense enough to compensate for darker months in equatorial regions. Warmth and rainfall supported year-round productivity. Bone histology studies reveal rapid growth rates in many dinosaur species. Microscopic examination of growth rings suggests that some dinosaurs grew as quickly as modern mammals. This challenges outdated views of dinosaurs as sluggish reptiles. In a greenhouse world, elevated metabolic rates would have been advantageous. Respiratory efficiency in dinosaurs may also have contributed to their success. Evidence from fossilized skeletons indicates air sac systems similar to those in modern birds. Such systems allow for more efficient oxygen extraction. In warm climates, efficient respiration aids in thermoregulation and sustained activity. The greenhouse atmosphere itself may have influenced physiology. Although oxygen levels during the Cretaceous were not dramatically higher than today, stable, warm conditions reduced environmental stress associated with cold climates. Dinosaurs did not need to contend with prolonged freezing temperatures across much of the globe. Ecosystems were structured around complex food webs. Flowering plants supported diverse insect populations. Beetles, flies, and early pollinators thrived. Insects, in turn, provided food for small theropods and early birds. Mammals, though generally small, diversified quietly beneath dinosaur dominance. River systems meandered across low-relief landscapes. With sea levels high, many continents had broad coastal plains. These areas were rich in sediments and nutrients. Seasonal flooding deposited fertile soils that sustained dense vegetation. Inland environments varied. Some continental interiors experienced seasonal dryness due to atmospheric circulation patterns. Monsoonal systems driven by warm oceans could create alternating wet and dry periods. But even in these regions, extreme cold was absent. Predator-prey dynamics in such productive systems would have been intense. Large herbivore populations required regulation. Theropods evolved keen senses, strong limbs, and powerful jaws. Pack hunting behaviors have been hypothesized for some species, though evidence remains debated. The distribution of dinosaur species was influenced by continental drift. Although Pangaea had broken apart long before, remnants of its configuration shaped Cretaceous geography. Land connections between certain continents allowed faunal exchanges. As continents drifted further apart, evolutionary lineages diverged, South America and Africa, though separating, shared similar dinosaur faunas early in the Cretaceous. Later isolation led to distinct evolutionary paths. India's northward journey across the Tethys Ocean carried unique species that would eventually encounter Asian faunas after collision. The greenhouse climate also influenced vegetation structure, and as regions in warmer conditions, forest canopies may have been denser in some regions. This created stratified habitats supporting arboreal species. Small theropods with feathered bodies likely navigated these environments with agility. Feathers themselves, once thought exclusive to birds, are now known to have been widespread among theropods. Insulation may have been important even in warm climates, particularly for juveniles or high-latitude species experiencing cooler seasonal temperatures. The interaction between climate and body size is complex. In modern ecosystems, some animals grow larger in colder climates as a means of conserving heat. But in the Cretaceous, gigantism among herbivores was likely driven more by ecological opportunity than temperature alone. Abundant vegetation allowed selection to favor large body sizes that deterred predators and enhanced digestive efficiency. Digesting tough plant material requires extended fermentation in large guts. Enormous body size facilitates this, and titanosaurs and other sauropods exemplify this strategy. Their long necks allowed them to exploit vast feeding ranges without moving their massive bodies frequently, conserving energy. The greenhouse Earth also shaped reproductive strategies. Warm climates reduce egg incubation constraints. Many dinosaurs laid eggs in nests, exposed to ambient conditions. In the absence of freezing temperatures, egg survival rates may have been higher in many regions. Fossil nesting sites provide evidence of colonial breeding in some species. This suggests social behaviors adapted to stable environmental conditions. Repeated use of nesting grounds implies predictable climate patterns over generations. As flowering plants, diversified co-evolutionary relationships likely intensified. Insects adapted to pollinate specific plant species. Plants evolved traits to attract pollinators. This accelerated biodiversity across ecosystems. While dinosaurs dominated visually, they were part of broader communities. Crocodilians thrived in warm river systems. Turtles inhabited freshwater and marine environments. Pterosaurs soared above coastlines and inland seas, feeding on fish and small animals. Birds, descendants of small theropods, diversified alongside their dinosaur relatives. In a greenhouse world with minimal cold stress, avian lineages could expand into varied niches. Some species likely inhabited polar forests, exploiting insect-rich summer seasons. The absence of large ice sheets meant that mountain glaciers were limited. Alpine environments existed, but were not dominated by ice. Precipitation at higher elevations would have fallen as rain more often than snow in many regions. This created expansive lowland ecosystems uninterrupted by glacial barriers. Migration routes were open, genetic exchange between populations occurred more readily, biodiversity flourished in interconnected habitats. However, greenhouse climates also bring vulnerabilities. High temperatures increase evaporation, which can intensify drought in some continental interiors. Sedimentary evidence indicates episodic aridity in certain regions. Dinosaurs and other animals would have needed behavioral or physiological adaptations to survive these fluctuations. Some fossil deposits reveal mass mortality events, possibly linked to drought or flooding. River systems in warm climates can be highly dynamic. Flash floods following intense rainfall can reshape landscapes quickly. Still, compared to periods marked by glaciation and repeated climatic oscillations, the mid-Cretaceous was relatively stable. This long interval of warmth allowed ecosystems to reach equilibrium states rarely sustained for such duration. The equability of the greenhouse world meant that temperature differences between equator and poles were smaller. This reduced latitudinal climate barriers, and species ranges could extend further north and south than today. Isotopic analyses of dinosaur teeth provide insight into their habitats. Oxygen isotope ratios can reflect the temperature of drinking water, offering clues about local climates. Such studies support the idea of mild, high-latitude conditions. The terrestrial greenhouse world was not static. Volcanic eruptions occasionally altered atmospheric composition. Ash layers preserved in sedimentary rocks record such events, but these were transient compared to the overarching warm baseline. Over millions of years, tectonic movements gradually altered geography. Mountain ranges rose, Ocean gateways shifted. Subtle changes in circulation began setting the stage for eventual cooling trends. But during the peak greenhouse, terrestrial life thrived under consistent warmth. If one were to walk across a Cretaceous floodplain, the sensory experience would be overwhelming. Humid air, heavy with the scent of vegetation. Insects buzzing in dense clouds. Distant calls of large herbivores. The ground trembling as a herd of hadrosaurs passes towering conifers filtering golden sunlight. Predators would move with calculated stealth. Tyrannosaurs, though primarily associated with later Cretaceous North America, symbolizes the culmination of theropod evolution in this warm world. Its binocular vision and massive jaw strength reflect an apex predator honed in competitive ecosystems. Spinosaurus represents another dimension of adaptation. Exploiting aquatic niches, it demonstrates how greenhouse climates expanded ecological possibilities. Warm, shallow waters supported fish populations large enough to sustain such specialized predators. This terrestrial dominance of dinosaurs did not arise solely from climate, but climate provided the stable stage upon which evolutionary innovation unfolded. Chapter 4 reveals a world in full biological expansion. Forests dense and widespread, herbivores massive and numerous, predators refined and powerful, insects diversified, birds evolving, mammals diversifying quietly in shadow, all under a sky thick with greenhouse gases, all in a world without permanent winter. The endless summer-shaped physiology, behavior, and evolutionary pathways it fostered gigantism, specialization, and ecological complexity. But tectonic forces continued to move beneath this flourishing biosphere. The same processes that created the greenhouse world would eventually alter it. For now, the land belonged to dinosaurs, thriving in warmth that stretched from equator to pole. The era of endless summer was at its height. While forests spread to the poles and dinosaurs ruled continents under endless warmth, the true architect of the greenhouse world operated far beneath the surface. Invisible to every creature that walked, flew, or swam, tectonic forces reshaped the planet from below. The era when summers never ended was not an accident of weather. It was the product of deep Earth processes that altered the atmosphere, oceans, and geography over tens of millions of years. To understand the greenhouse Cretaceous, we must descend beneath soil, beneath bedrock, into the slow mechanics of plate tectonics. Earth's outer shell is divided into massive plates floating atop the semi-fluid asthenosphere. These plates move at rates comparable to the growth of fingernails. Yet over millions of years, they rearrange entire continents. Their collisions build mountains. Their separations create oceans. And their interactions regulate the long-term carbon cycle. Long before the Cretaceous greenhouse reached its peak, the supercontinent Pangaea had already fragmented. But the breakup did not end abruptly. Continental rifting continued through the Jurassic and into the Cretaceous. As land masses separated, new ocean basins opened. When continents pull apart, mid-ocean ridges form. These are underwater mountain chains where magma rises continuously from the mantle. As molten rock cools, it forms new oceanic crust. This process is called sea-floor spreading. During the mid-Cretaceous, sea-floor spreading rates were unusually high. Geological reconstruction suggests that oceanic crust was being generated at accelerated speeds. More spreading means more volcanic activity, and more volcanic activity means more carbon dioxide released into the atmosphere. Volcanoes are among Earth's most powerful carbon sources. While individual eruptions may inject ash and short-term cooling aerosols, sustained volcanic outgassing over millions of years increases atmospheric carbon dioxide. This gas traps infrared radiation, strengthening the greenhouse effect. Large igneous provinces also played a major role. These are enormous volcanic regions where vast quantities of basaltic lava erupt over relatively short geological timescales. During the Cretaceous, several such provinces formed, including the Ontong Java Plateau in the Pacific Ocean. The Ontong Java Plateau alone represents one of the largest volcanic outpourings in Earth's history. The scale of these eruptions is difficult to comprehend. Lava flows covered areas comparable to entire modern countries beneath the ocean. Thick basalt accumulated in layers thousands of meters deep. Each pulse of volcanic activity injected carbon dioxide into the atmosphere, reinforcing global warmth. The configuration of continents also influenced ocean circulation. In the early Cretaceous, many ocean gateways were narrower than today. The Atlantic Ocean was still relatively young and narrower. India had not yet collided with Asia. Antarctica was not fully isolated at the South Pole. These geographic differences altered current patterns. Warm equatorial waters circulated more freely toward higher latitudes. Without a fully developed circumpolar current around Antarctica, there was no strong mechanism to thermally isolate the southern continent. Today, the Antarctic circumpolar current acts as a thermal barrier, keeping Antarctica cold and helping maintain its ice sheet. In the Cretaceous, such a current did not exist. Warm waters bathed polar regions, preventing ice formation. Continental positions also influenced albedo. Large land masses situated near the equator absorb more solar radiation than those at higher latitudes. During the Cretaceous, much continental area lay within tropical and subtropical zones, enhancing heat absorption. Tectonic uplift and mountain building affect climate through chemical weathering. When mountains rise, fresh rock is exposed to rainfall. Chemical reactions between silicate minerals and carbonic acid remove carbon dioxide from the atmosphere. This weathering process acts as a long-term thermostat. However, during periods of intense volcanic outgassing and rapid seafloor spreading, carbon input can exceed removal rates. This appears to have been the case during peak greenhouse intervals of the Cretaceous. The carbon cycle during this time was dynamic. Volcanic emissions increased atmospheric carbon dioxide, enhanced warmth intensified the hydrological cycle, increased rainfall, accelerated weathering. Weathering transported dissolved ions to the oceans, where carbonate minerals formed and were buried as sediment. Over millions of years, this burial slowly reduced atmospheric carbon dioxide. But the lag between input and removal meant that high concentrations could persist for extended periods. Oxygen isotope analysis of marine carbonates reveals sustained high ocean temperatures. Carbon isotope excursions in sedimentary records reflect pulses of volcanic carbon entering the system. These geochemical signatures align with tectonic reconstructions of spreading rates. Another tectonic factor influencing greenhouse conditions was ocean basin volume. Newly formed oceanic crust is hotter and therefore more buoyant. When seafloor spreading rates are high, a larger proportion of ocean crust is young and elevated. This reduces the volume of ocean basins and displaces seawater onto continents, raising sea levels. This mechanism helps explain why global sea levels were so high during the Cretaceous. Not only was water expanded thermally due to warmth, but ocean basins themselves were shallower because of extensive young crust. The flooding of continental interiors created vast shallow seas. These seas influenced climate by moderating temperatures and increasing evaporation. They also provided additional sites for carbonate deposition, contributing to long-term carbon sequestration. Tectonics also influenced atmospheric circulation indirectly. The arrangement of continents affects wind patterns, monsoons, and precipitation distribution. With continents fragmented and seas widespread, atmospheric circulation during the Cretaceous differed significantly from today. Climate models suggest weaker equator-to-pole temperature gradients resulted in weaker jet streams. Storms may have been distributed differently. Rainfall patterns were shaped by proximity to shallow seas rather than large ice sheets. The greenhouse world, therefore, was not simply the result of elevated carbon dioxide. It was the outcome of an integrated system involving tectonic geometry, volcanic activity, ocean chemistry, and atmospheric physics. Over tens of millions of years, subtle tectonic shifts began to alter this balance. As the Atlantic Ocean widened, new circulation pathways formed. As India continued its northward journey, the Tethys Ocean narrowed. As Australia gradually separated from Antarctica, ocean gateways evolved. These changes would eventually contribute to cooling trends in the later Cretaceous and early Paleogene. But during the peak greenhouse, tectonic processes maintained warmth. Consider the Untung Java Plateau once more. Its eruption likely released vast quantities of carbon dioxide over a geologically brief interval. This could have triggered oceanic anoxic events by increasing temperatures and altering ocean stratification. Sedimentary layers corresponding to these events show elevated organic carbon content and distinct isotopic signatures. They are markers of tectonic pulses influencing climate. Mountain building elsewhere also influenced regional climates. Uplift can create rain shadows, altering precipitation patterns. Though major mountain ranges like the Himalayas had not yet formed, smaller uplifts shaped local environments. Tectonics determines the position of continents relative to ocean currents. When continents block, or redirect currents, climate can shift dramatically in the Cretaceous. The lack of a strong circumpolar barrier around Antarctica allowed warm water to circulate freely around high southern latitudes. Eventually, as continents drifted further apart and ocean gateways widened, new current systems would emerge. But during this chapter of Earth's history, tectonic configuration favored warmth. The interplay between deep Earth processes and surface climate demonstrates the interconnectedness of planetary systems. Magma rising from the mantle influences atmospheric composition. Atmospheric composition alters temperature. Temperature shapes ecosystems. No dinosaur walking through a Cretaceous forest could perceive the mid-ocean ridge thousands of kilometers away, injecting carbon dioxide into the sky. Yet their entire world depended on it. The greenhouse state was sustained not by a single cause, but by converging factors: rapid seafloor spreading, large igneous provinces, continental fragmentation, high sea levels, and altered ocean circulation. These processes operated slowly by human standards, but rapidly in geological terms. Millions of years may seem vast, but within Earth's 4.5 billion year history, the Cretaceous greenhouse represents a specific climatic mode triggered by identifiable tectonic circumstances. Geological maps reconstructing Cretaceous continents reveal unfamiliar coastlines. North America's western interior seaway bisected the continent. Africa's outline differed markedly from today. Antarctica was not the isolated frozen continent we know. Such reconstructions are built from paleomagnetic data preserved in rocks. As molten rock cools at mid-ocean ridges, magnetic minerals align with Earth's magnetic field. These signatures provide a record of plate positions and spreading rates. From this evidence, scientists calculate how fast ocean basins expanded. These rates correlate with volcanic output estimates, supporting the link between tectonics and greenhouse conditions. The greenhouse Earth was therefore tectonically primed. High spreading rates and volcanic emissions elevated carbon dioxide. Continental positions allow heat retention. Absence of polar ice reinforcement. Over time, feedback mechanisms would slowly shift the balance. Increased weathering, changing ocean gateways, and declining volcanic output would eventually allow atmospheric carbon dioxide to decrease. But in Chapter 5, we remain within the heart of the greenhouse. Tectonic forces continue to pump carbon into the atmosphere. Sea levels remain high. Polar forests persist. Dinosaurs dominate land. Beneath the endless summer lies a restless planet, reshaping itself from within. Tectonics is the deep heartbeat of Earth in the Cretaceous. That heartbeat was rapid and powerful, sustaining one of the warmest extended climates of the last half-billion years. The surface world of forests and giants was built upon magma and drifting continents. And as those continents continued their slow rearrangement, the conditions sustaining endless summer would begin, almost imperceptibly, to change. But for now, the greenhouse remains strong. The engine of warmth still burns beneath the crust. Endless summer does not mean eternal stability. Even in a greenhouse world sustained by tectonic fire and elevated carbon dioxide, the climate system remained sensitive to disturbance. Warmth, when pushed beyond certain thresholds, constrain the chemistry of oceans, the resilience of ecosystems, and the balance of atmospheric circulation. Beneath the flourishing forests and dinosaur-dominated plains, subtle hazards were building. The Cretaceous greenhouse was not a uniform paradise. It contained episodes of stress, some regional, some global. These stresses reveal that even during extended warm intervals, Earth's systems can approach tipping points. One of the most significant vulnerabilities of a warm ocean is oxygen availability. Oxygen dissolves less efficiently in warmer water. As sea surface temperatures rise, the amount of oxygen that can be held in solution declines. This alone does not create catastrophe, but combined with other factors, it can destabilize marine ecosystems. In the Cretaceous, enhanced weathering from intensified rainfall delivered nutrients such as phosphorus and nitrogen into shallow seas. Nutrient enrichment can stimulate plankton growth. On the surface, this appears beneficial. More plankton means more primary productivity. But when plankton blooms die, they sink. Their decomposition consumes oxygen in deeper waters. If circulation is sluggish, oxygen is not replenished efficiently. Over time, deep waters can become hypoxic or even anoxic. This process is recorded in sedimentary rocks as dark, organic rich layers known as black shales. Several major oceanic anoxic events occurred during the Cretaceous. These were intervals when large portions of the world's oceans experienced oxygen depletion. Geochemical signatures from these layers show elevated carbon burial and distinct carbon isotope excursions. These isotopic shifts suggest massive disturbances in the carbon cycle, likely linked to volcanic pulses and climatic warming. During these events, marine organisms sensitive to low oxygen conditions declined. Some species disappeared regionally. Reef systems suffered in certain basins, yet life did not collapse globally. Instead, ecosystems reorganized. Coral reefs, in particular, are sensitive to changes in temperature and chemistry. Although reefs flourished in many parts of the Cretaceous, there were intervals of reef decline associated with extreme warmth or chemical shifts in seawater. Ocean acidification is another hazard in greenhouse climates. When atmospheric carbon dioxide dissolves into seawater, it forms carbonic acid. This lowers pH and can make it more difficult for organisms to build calcium carbonate shells and skeleton. In the Cretaceous, carbonate-producing organisms such as coccolithophores and rudist bivalves played major roles in reef construction. During peak volcanic intervals, increased carbon dioxide may have temporarily stressed these communities. Yet the resilience of Cretaceous ecosystems suggests adaptation to a high-carbon baseline. The rate of change, rather than absolute concentration alone, likely determines severity. On land, heat presents its own challenges. While warm climates can enhance plant growth, extreme heat combined with seasonal dryness can trigger drought. Sedimentary records from some continental interiors show evidence of episodic aridity. Monsoonal systems driven by warm seas could create alternating wet and dry seasons. River deposits indicate fluctuating water levels. Some fossil assemblages suggest mass mortality events potentially linked to drought stress. Wildfires may have been more common in certain regions. Charcoal fragments preserved in sediments indicate that fire was part of Cretaceous ecosystems. Elevated oxygen levels were not dramatically higher than today, but warm, dry intervals would have increased fire frequency. Fire, however, is not purely destructive. It can reset ecosystems, open space for new plant growth, and influence evolutionary trajectories. Some plant lineages may have adapted to periodic burning. Heat also affects animal physiology. Large-bodied dinosaurs, despite their advantages, would have needed mechanisms for thermoregulation. Evidence suggests that many theropods possessed air sac systems that improved respiratory efficiency and heat dissipation. Behavioral adaptations likely included seeking shade, altering activity patterns, or utilizing water bodies for cooling. Spinosaurus, with its semi-aquatic lifestyle, represents one extreme adaptation to warm environments. Another subtle hazard in greenhouse climates is methane release. Warm ocean temperatures can destabilize methane hydrates stored in marine sediments. When released, methane acts as a powerful greenhouse gas. Although direct evidence for large-scale methane-driven events in the mid-Cretaceous is debated, carbon isotope excursions during some anoxic events hint at possible methane involvement. If methane contributed, it would have amplified warming in feedback loops. The hydrological cycle intensified under greenhouse conditions. Warmer air holds more moisture. Increased evaporation from warm seas fed stronger precipitation systems. This meant heavier rainfall in some regions and potentially more intense storms. Without strong equator-to-pole temperature gradients, jet streams were weaker. Storm tracks may have been less predictable. Tropical cyclones over warm seas could have been powerful due to elevated sea surface temperatures. Coastal regions, already expanded by high sea levels, would have been vulnerable to storm surges. Shallow inland seas could experience rapid salinity changes depending on rainfall and evaporation balance. In polar regions, though temperatures were mild, ecosystems still faced stress from prolonged winter darkness. Animals had to survive months without sunlight-driven plant growth. While temperatures did not plunge into extreme cold, energy availability declined seasonally. Bone growth patterns in polar dinosaurs show pauses corresponding to dark periods, suggesting seasonal metabolic adjustments. This indicates that even in a greenhouse world, environmental rhythms impose constraints. Tectonic activity also introduced episodic hazards. Volcanic eruptions could inject aerosols into the atmosphere, causing short-term cooling. Ashfall could smother vegetation regionally. Lava flows could reshape landscapes. Large igneous province eruptions may have triggered some anoxic events by rapidly increasing atmospheric carbon dioxide. These events illustrate how the greenhouse system could be destabilized by pulses of carbon input. The greenhouse Earth, therefore, operated within boundaries. It was warm and stable on average, but sensitive to perturbation. The absence of ice sheets did not mean the absence of climatic stress. Geochemical records indicate that carbon dioxide levels fluctuated within the Cretaceous. Not every million-year interval was identical. There were peaks and slight declines. These variations influenced temperature, sea level, and ocean chemistry. Over tens of millions of years, slow drawdown of carbon through weathering and burial began to counterbalance volcanic emissions. The system gradually approached thresholds where cooling trends could emerge. But before that transition, life continued adapting to warmth and intermittent stress. Ecosystems are dynamic. Following an anoxic event, surviving species radiate into vacated niches. Evolutionary innovation accelerates under pressure. The Cretaceous fossil record shows pulses of diversification after environmental disturbances. This resilience demonstrates that greenhouse climates do not automatically equate to collapse. Life can persist and adapt under high carbon dioxide and elevated temperatures. However, stability is contingent on the rate of change. Geological transitions unfold over millions of years, allowing evolutionary processes time to respond. As Chapter 6 unfolds, subtle tectonic shifts begin altering ocean gateways. Volcanic activity patterns change. Spreading rates slowly decline. These processes reduce carbon input relative to removal. Weathering of newly uplifted terrains gradually increases. Carbonate burial continues. Atmospheric carbon dioxide begins a slow descent from peak levels. The climate does not flip abruptly from greenhouse to icehouse. Instead, it moves gradually toward a cooler equilibrium, but the greenhouse state remains dominant through much of the Cretaceous. Even as hazards emerge, forests still stretch toward the poles. Inland seas remain expansive. Dinosaurs continue to thrive. The greenhouse world teaches that warmth contains internal stresses. Oxygen depletion, acidification, drought, storms, and volcanic pulses are part of its fabric. Earth's climate is not binary. It exists along a continuum of states shaped by deep time processes. In the Cretaceous, that state favored warmth and biological abundance, yet it also flirted with chemical instability. The balance between carbon input and removal, between ocean circulation and stagnation, between productivity and oxygen depletion, defined this era, and as tectonic engines slowly adjusted, the long arc of climate would begin bending away from its peak. The endless summer was powerful, but not permanent. The system was already preparing for change, even if no creature alive at the time could sense it. Deep beneath the surface, the forces of cooling were gathering strength. No climate state lasts forever. Even the most prolonged greenhouse interval is part of a larger planetary rhythm. By the later stages of the Cretaceous, subtle forces were reshaping the balance that had sustained endless summer for tens of millions of years. The shift was gradual, almost imperceptible at first. But beneath the forests, beneath the inland seas, beneath the dinosaur-dominated plains, The thermostat of the planet was slowly turning. To understand this transition, we must return to the carbon cycle. The greenhouse world was maintained by a dynamic equilibrium between carbon sources and carbon sinks. Volcanic outgassing and rapid seafloor spreading injected carbon dioxide into the atmosphere. Weathering of silicate rocks, burial of organic carbon, and carbonate deposition removed it. During peak mid-Cretaceous warmth, carbon input outpaced removal, atmospheric carbon dioxide remained high, sustaining elevated temperatures and ice-free poles. But tectonic systems are not static. Spreading rates fluctuate. Volcanic pulses wax and wane over millions of years. Mid-ocean ridge activity began to slow compared to its earlier intensity. Fewer massive volcanic outpourings meant reduced long-term carbon injection. At the same time, other processes strengthened carbon removal. As continents continued drifting, new mountain-building episodes exposed fresh rock to chemical weathering. When silicate minerals react with carbonic acid formed from dissolved carbon dioxide in rainwater, they convert atmospheric carbon into stable carbonate minerals. This reaction draws carbon dioxide from the atmosphere over geological timescales. Even modest increases in weathering rates can, over millions of years, significantly reduce atmospheric carbon concentrations. Another factor was organic carbon burial. The Cretaceous oceans, especially during anoxic events, preserved large amounts of organic matter in sediments. When organic carbon is buried rather than oxidized back into carbon dioxide, it effectively removes carbon from the atmospheric system. Black shale deposits formed during oceanic anoxic events represent large-scale carbon sequestration. Although these events were triggered by warming and instability, their aftermath contributed to long-term carbon drawdown. Over time, this cumulative burial slowly reduced greenhouse gas levels. Tectonic geography also evolved. The Atlantic Ocean widened. India moved closer to Asia. Australia began to separate more decisively from Antarctica. As ocean gateways shifted, circulation patterns changed. The eventual development of new current systems would have profound consequences. While the full isolation of Antarctica and establishment of a circumpolar current occurred later in the Cenozoic, the groundwork for changing ocean dynamics began in the late Cretaceous. Subtle adjustments in ocean circulation can alter heat distribution across the planet. If warm water transport to polar regions decreases, high-latitude cooling can begin. Temperature reconstructions from oxygen isotope data indicate that by the late Cretaceous, global temperatures, while still warm relative to today, had begun trending downward from peak mid-Cretaceous values. Polar regions remained forested. Sea levels were still high. Dinosaurs still dominated. But the intensity of greenhouse conditions was moderating. Carbonate deposition continued in shallow seas. Microscopic organisms such as coccolithophores built calcium carbonate shells that accumulated on the seafloor. Thick chalk formations formed over millions of years. The White Cliffs of Dover are composed largely of such deposits from this era. Each layer of chalk represents countless microscopic shells, each one incorporating carbon from the atmosphere into mineral form. Collectively, these deposits represent massive long-term carbon storage. The interplay between volcanic decline and carbonate burial slowly reduced atmospheric carbon dioxide. This did not create immediate glaciation. Instead, it nudged the planet toward a cooler equilibrium. Cooling in a greenhouse world does not begin with ice sheets forming overnight. It begins with subtle shifts in temperature, gradients in seasonal patterns, in ocean chemistry. Climate models suggest that as carbon dioxide decreases, polar amplification weakens. Temperature differences between equator and poles gradually increase. Cooler polar summers reduce annual mean temperatures. Snow that once melted completely each year may begin lingering slightly longer in some regions. However, during the late Cretaceous, permanent continental ice sheets had not yet formed. The world was still fundamentally warm. Vegetation patterns may have shifted slightly. Some plant communities could have migrated equatorward in response to incremental cooling. Species adapted to peak warmth might have faced new pressures. Dinosaurs themselves continued evolving. Large herbivores and apex predators diversified further. Tyrannosaurus, appearing near the very end of the Cretaceous, represents the culmination of theropod evolutionary trends within a still warm but gradually moderating climate. Marine ecosystems also reflected change. Some reef communities declined in certain basins. Shifts in ocean chemistry and circulation influenced species distributions. As carbon dioxide declined, ocean acidity would have adjusted accordingly. Subtle increases in pH could alter carbonate saturation states, influencing shell-building organisms. The hydrological cycle, so intensified under peak greenhouse conditions, may have moderated slightly. Regional precipitation patterns adjusted. Some areas might have experienced reduced rainfall compared to earlier Cretaceous intervals. Tectonic collisions were also beginning to reshape the future climate trajectory. India's northward movement would eventually culminate in collision with Asia, forming the Himalayas. Though this occurred after the Cretaceous, the motion was already underway. Such collisions increase weathering rates dramatically, enhancing long-term carbon drawdown. The late Cretaceous, therefore, represents a transitional chapter. The greenhouse world was not collapsing, but it was evolving. If one could stand on a late Cretaceous floodplain, the world would still appear lush and warm. Inland seas still shimmered beneath humid skies. Polar forests still stood. Dinosaurs still roamed. Yet the deep system beneath this landscape was shifting. Carbon input was no longer at peak intensity. Sinks were gaining relative strength. Earth's climate operates like a vast balancing mechanism with delayed feedback. Once greenhouse conditions are established, reversing them requires sustained changes in carbon flux over millions of years. By the final few million years of the Cretaceous, global temperatures were likely several degrees lower than peak mid-Cretaceous values, though still significantly warmer than today. Sea levels may have fallen slightly as ocean crust cooled and subsided. As newly formed crust ages, it becomes denser and sinks deeper into the mantle, increasing ocean basin volume and lowering global sea level modestly. This slow regression of shallow seas altered coastal ecosystems. Habitats that had existed for millions of years began shrinking. Species adapted to shallow marine environments faced new constraints. The western interior seaway in North America, once expansive, gradually narrowed. Sediment filled its basin by the very end of the Cretaceous. Much of it had retreated. These geographic changes reshaped migration routes and food webs. Terrestrial animals gained access to new corridors, and marine habitats contracted. The cooling trend alone was not catastrophic. It was gradual enough to allow ecosystems to adjust. Dinosaurs continued thriving. Forests remained extensive, but the system had lost some of its greenhouse intensity. The endless summer was no longer at its zenith. Carbon dioxide levels were likely declining toward lower thresholds, though still elevated compared to modern pre-industrial levels. The planet was transitioning from a super greenhouse toward a milder greenhouse. Such transitions are part of Earth's long-term oscillation between greenhouse and icehouse states. Over hundreds of millions of years, the planet alternates between warm intervals without polar ice and cooler intervals with extensive glaciation. The late Cretaceous was moving toward a cooler phase, though not yet an icehouse. No creature walking the Earth at that time could foresee the sudden event that would soon disrupt this slow cooling trajectory. For tens of millions of years, climate change had been gradual, governed by tectonics and carbon cycling. Then, in an instant, on geological timescales, an external force would intervene. Chapter 7 stands at the threshold. The greenhouse world is still alive, but its intensity has softened. Tectonic engines are shifting gears. Carbon burial is gaining strength. Shallow seas are retreating slightly. Dinosaurs rule a world that is beginning, slowly, to cool. The era of endless summer is entering its final act. Not because of gradual tectonic drift alone, but because an event from beyond the planet is approaching. The system, already adjusting, is about to face a shock unlike any in its recent history. The slow cooling of the late Cretaceous sets the stage for a dramatic transformation. And in that transformation, the greenhouse world will meet its end. For millions of years, the greenhouse world had endured. Tectonic forces had built it. Volcanic breath had sustained it. Forests had spread to the poles, inland seas had divided continents, and dinosaurs had ruled beneath skies thick with carbon dioxide. The slow cooling of the late Cretaceous had begun, but it was gradual, measured in millions of years. Then, in a single day, everything changed. 66 million years ago, an asteroid, roughly 10 to 12 kilometers wide, approached Earth on a collision course. It was not part of the slow rhythms of tectonics or carbon cycling. It was an external shock, abrupt and violent. The impact site lay in what is now the Yucatan Peninsula of Mexico. The crater it created is known today as the Chicxulub crater. Buried beneath sediment, it spans more than 180 kilometers in diameter. When the asteroid struck, it released energy equivalent to billions of atomic bombs. Rock vaporized instantly. Shock waves radiated outward at supersonic speeds. Forests ignited hundreds of kilometers away. Molten debris was blasted into the upper atmosphere and beyond. Within minutes, a plume of superheated rock and gas rose above the planet. Ejecta fell back through the atmosphere as incandescent fragments, heating the sky globally. Some models suggest that re-entering debris generated enough thermal radiation to ignite widespread wildfires across continents. Tsunamis hundreds of meters high raced across nearby oceans. Coastlines were obliterated. Shallow seas churned violently. Sediment layers around the world record this moment as a thin band enriched in iridium, a rare element more common in asteroids than in Earth's crust. The greenhouse world, already in slow transition, now faced a catastrophic perturbation. Dust, soot, and sulfate aerosols injected into the atmosphere block sunlight. Photosynthesis depends on light. As darkness spread, plant productivity collapsed. The duration of this impact winter remains debated, but estimates range from months to several years of severely reduced sunlight. Temperatures dropped rapidly. The same greenhouse atmosphere that had sustained warmth could not prevent sudden cooling when solar radiation was cut off. This was not gradual climate change. It was abrupt, extreme, and global. Herbivorous dinosaurs, dependent on plant life, faced immediate crisis. With vegetation dying back, food chains destabilized, carnivorous dinosaurs soon followed as prey populations declined. Marine ecosystems also suffered. Plankton, the base of ocean food webs, rely on sunlight. Reduced photosynthesis disrupted marine productivity. Some plankton groups experienced mass extinction. The fossil record marks this boundary clearly. It is known as the KPG boundary, formerly called the KT boundary. Above it, non-avian dinosaurs disappear. Below it, they dominate. The asteroid impact did not merely cool the planet. The vaporized rock containing sulfur compounds may have formed sulfate aerosols, contributing to acid rain. This would have further stressed terrestrial and marine ecosystems. Global wildfires released additional carbon dioxide and soot. Yet despite this pulse of greenhouse gas, the immediate effect was cooling due to sunlight blockage. In a matter of years, the greenhouse world that had persisted for tens of millions of years was plunged into a temporary planetary winter. Forests that had flourished even at polar latitudes suffered catastrophic losses. Large-bodied animals requiring substantial food resources were particularly vulnerable. Non-avian dinosaurs vanished. Pterosaurs disappeared. Many marine reptiles went extinct. Ammonites, which had thrived through previous environmental fluctuations, did not survive this event. However, not all life perished. Birds, descendants of small theropod dinosaurs, survived. Small mammals endured. Crocodilians persisted. Turtles and some fish lineages survived. Why did some groups survive while others did not? Body size likely played a role. Smaller animals require fewer resources and can survive on limited food supplies. Burrowing behavior may have offered protection from heat pulses and environmental extremes. Dietary flexibility would have been advantageous. Mammals, though relatively small during the Cretaceous, were diverse in ecological niches. Some may have fed on insects, seeds, or detritus less dependent on live vegetation. Birds capable of flight could relocate in search of resources. Some may have fed on seeds that persisted through the impact winter. The asteroid did not reverse the long-term cooling trend already underway. Instead, it imposed an abrupt shock atop that trajectory. After dust settled and sunlight gradually returned, ecosystems began rebuilding, but the greenhouse world of dinosaurs was gone. Carbon dioxide levels likely fluctuated in the aftermath. Wildfires and ocean changes altered atmospheric composition, yet the long-term tectonic and weathering trends continued drawing carbon downward. Without dinosaurs dominating terrestrial ecosystems, new opportunities emerged. Mammals began diversifying rapidly in the Paleocene. Forests regenerated, though species composition changed. Flowering plants continued expanding. Birds diversified into new ecological roles. Marine ecosystems also reorganized. New plankton communities arose. Coral reefs eventually recovered in different forms. The impact marked the end of the Cretaceous greenhouse dynasty, but it did not instantly transform Earth into an icehouse world. The early Paleogene remained relatively warm compared to modern conditions. Greenhouse gases were still elevated relative to today. Polar regions did not immediately freeze. However, without sustained high volcanic outgassing and with continued carbon burial, the long arc of climate continued bending toward cooler states. Over tens of millions of years following the impact, tectonic changes intensified cooling. India's collision with Asia uplifted the Himalayas, accelerating silicate weathering and carbon removal. Australia's separation from Antarctica enabled the formation of the Antarctic circumpolar current, thermally isolating the southern continent. Eventually, permanent ice sheets formed on Antarctica in the Oligocene roughly 34 million years ago. The planet entered a new climatic regime, transitioning from greenhouse to icehouse. The era when summers never ended had concluded not solely because of the asteroid, but because the underlying tectonic and carbon cycles were already shifting. The asteroid acted as a punctuation mark, ending the dominance of dinosaurs and reshaping biological evolution. The greenhouse world demonstrated that Earth can exist in radically different states depending on atmospheric composition and continental configuration. For tens of millions of years, high carbon dioxide, rapid seafloor spreading, and favorable ocean circulation eliminated polar ice and created equable climates. Then, gradual carbon drawdown initiated cooling, and finally, an extraterrestrial impact delivered a sudden shock that reset ecological systems. The fossil record preserves this transformation layer by layer. Below the boundary, forests stretch to the poles, and dinosaurs roam abundant landscape. Above it, mammals diversify, and birds take to the skies in new form. The greenhouse Earth was not fragile in the sense of being easily disrupted by internal variability. It endured multiple volcanic pulses and oceanic anoxic events, but it was vulnerable to sudden external forces. If one could stand at the moment just before the asteroid's arrival, the world would appear stable, perhaps even eternal in its warmth. Dinosaurs would move across floodplains. Polar forests would sway beneath continuous summer light. Inland seas would shimmer under humid skies. No visible sign would warn of the incoming object streaking silently through space. The transition from endless summer to global crisis occurred faster than any tectonic process. In geological terms, it was instantaneous. Yet from that devastation emerged a new world. The extinction of non-avian dinosaurs opened ecological space that mammals would eventually fill. Primates would evolve. Eventually, humans would appear, studying sediment layers and reconstructing this ancient greenhouse epoch. Chapter 8 closes the story of the era when summers never ended. It began with tectonic fire and elevated carbon dioxide. It expanded oceans and forests to the poles. It nurtured giants and complex ecosystems. It slowly moderated as carbon cycles shifted, and it ended abruptly with a celestial impact that reshaped life on Earth. The greenhouse world is not a myth. It is written in isotopes, in chalk cliffs, in fossil forests buried beneath Antarctic ice, and in the iridium layer marking a boundary between ages. Earth is capable of profound climatic transformation. It has lived without ice at its poles. It has sustained forests in darkness and warmth at the ends of the world. And it has endured sudden catastrophe, only to regenerate in new forms. The era of endless summer was one chapter in the long, dynamic story of our planet. A chapter of warmth, abundance, instability, and ultimate change. The story does not end here. It continues in the Icehouse world that followed, and in the climate decisions that shape our own future.